So far, we've talked about two ways of representing a graph. Right? One way is to just list all of the pairs of vertices that represent the edges, and another way is by drawing a picture. In this lecture, we're going to talk about a third method called the matrix representation of a graph that is particularly common in a lot of computer applications, especially the kinds of things that you're going to be thinking of if you're coming at this from a computer science perspective. So a matrix is a two-dimensional equivalent of a sequence. So every value, instead of having just one index, has two. You can see that going on in my example here. The matrix and the entry in the upper left-hand corner, for example, the one that is in row 1, column 1, I've labeled A sub 1, 1. A sub 1, 2 is the value in row 1, column 2, and so forth. And now, we often identify matrices based on their size. For example, I would describe this matrix here as being a 2 by 3 matrix, since it has 2 rows and 3 columns. This example, 3 rows and 3 columns, so it's a 3 by 3 matrix, is what we call a square matrix. Right? A square matrix is one where the number of rows and the number of columns are the same. And in this kind of matrix, there's a special designation within it. Every value whose first and second index is the same, those are the ones on this line here, A sub 1, 1, A sub 2, 2, and so on. That's what's called the main diagonal of the matrix. Okay, so how can we actually do this? Right? How can we actually take a graph and get its matrix representation? Well, looking first specifically at a directed graph, what I'm going to do is I'm going to go to the entry that corresponds to the row of the from vertex and the column of the to vertex, and put a number there that tells me the number of edges going from and to those particular vertices. So look at vertex 1 and vertex 2. There are 2 edges going from vertex 1 and to vertex 2. So what I'm going to do over here in the matrix, I'm going to go from, that's going to be the row 1, to column 3, right? That corresponds to the receiving vertex, and that's where I'm going to put a 2, because there are 2 edges going from vertex 1 to vertex 2. Now suppose we have an undirected graph. Well, in some ways this is a little more straightforward. In cell A sub ij, I'm going to put the number of paths, number of edges, connecting vertex I to vertex j. So, there's a 2 here in the row 1, column 2 position, and that is because there are 2 edges going from vertex 1 to vertex 2. Now, how about the other way around? I mean, there's also 2 edges going from vertex 2 to vertex 1 because they're undirected, right? And yeah, down here in row 2, column 1, I also have a 2, right? So in a sense, every edge is being counted twice in the matrix. Once in this lower triangle, and a second time in this upper triangle. And if you look carefully at these, you'll see that one triangle's values do appear to be a mirror image of the other triangles. And that's not a coincidence. That's exactly the sort of behavior you should always see with an undirected graph. And if you flip back, you'll see that we did not see that with a directed graph. Right, so a graph that has this property, where it's kind of a mirror image of itself across that main diagonal, is what we call a symmetric graph, or excuse me, a symmetric matrix. Okay, a lot of examples there. We'll do a couple more videos with some specific examples. where we walk through in more detail that whole process of creating an adjacency matrix and of taking an adjacency matrix and going the other way, right, and drawing the graph that corresponds to it. Then in the next couple of lectures, we're going to look at some examples of things that we can do with these adjacency matrices.